Good afternoon. During the first part of the lecture today, I will present more examples of regular surfaces. The first example is actually not just one surface, but a class of surfaces. They are known as surfaces of revolution. So we consider a regular curve in the xz plane and we denote by C its trace. In order to study these surfaces, we make two assumptions. One, x of t positive for all t in AB, and the second one, c prime of t positive for all t in AB. If this is the z-axis and this is the x-axis, we have that if the assumption number one is satisfied, then we have that C does not intersect this axis here, and if z prime is positive, we have that C does not have self-intersection. So let's take, for example, this curve here. And let S denote the surface resulting when C is revolved about the z-axis. So in the case represented in this picture, the surface will be approximately looking like this one. So we want to show that S is a regular surface. So a natural surface patch is given by this formula, sigma of theta t. This is of x of t cosinus of theta, x of t sinus of theta, z of t. This map is nothing but then r theta gamma t. In other terms, it is the composition of a linear rigid motion represented by this matrix This rigid motion essentially is a rotation by an angle theta around the z-axis. Why the z-axis? Because you have the third row and the third column are 0, 0, 1. The image V equal sigma u, where u is this open set here, is open in S because it is the intersection with S of the open set R3, from which I remove the set of points of coordinate x, 0, z in R3 with x negative or 0. Sigma, the reason why this is true is that u is the product of minus pi, pi, and the interval AB. So this means that we are not considering, the image of u does not contain points such that x of t is equal to -1. Now you can prove easily that sigma is injective It remains to see that it's a diffeomorphism. Now, in order to do this, we have to check that sigma is smooth and that its inverse is smooth. Okay, sigma is clearly smooth because x of t and z of t are smooth. They are the component function of a regular curve. And cosinus of theta and sinus of theta are clearly smooth function. Now let's check that sigma inverse defined on V with values in U is smooth. This is true, and we will check this claim first on V plus, defined as the points of V such that x is positive. And on this subset of V, sigma inverse can be written down explicitly. So we have sigma inverse of x, y, z. This is given by the inverse of the tangent function evaluated at y over x, t of z, where t of z denotes the inverse of the function z of t. This function is smooth because it extends to the smooth function defined by the same formula. On the open set, which consists of all points of R3 with x positive and z in the interval ZA ZA, ZB. The smoothness of sigma inverse on other points of V is left as an exercise for you. So this implies that sigma is a surface patch. This patch covers not the entire surface S, but S except the curve along which it intersects that portion of the XZ plane where X is negative. The reason why this is true is that sigma is defined on minus pi cross AB, and it is given by this formula, sigma of theta t, this is x of t cosinus of theta, x of t sine of theta, z of t. So theta cannot take the value pi and minus pi, for which you have that cosinus of theta is minus 1, and in this case you would have that sigma is not equal to minus x of t, and since the sinus of theta would be 0, the image would be this point. And remember the fact that x of t is always positive, so this is always negative. And these points are located exactly on a plane for which x is negative. So in order to cover the points which are missed by this map, we use the same idea as the one in the example of the cylinder. So precisely we can consider the surface patch obtained by composing sigma with a rotation by pi about the z-axis. So this proves that S is a regular surface because we found two surface patches which together cover all of the points of S. Now we want to check that the Jacobian matrix at Q, at a generic point Q of sigma has a rank 2. We already know this is a consequence of the fact that S is regular, but we want to make the computation and to see this directly. So let's check that the sigma q, where q is a generic point theta t, has a rank 2. Okay, so the matrix which represents the sigma q is a matrix whose column are derivative of sigma with respect to theta and t, respectively. So we have minus x of t sinus of theta, x of t cosine of t is 0. I think I need more space. So I have x prime t cosine of theta, x prime of t sinus of theta, z prime of t. We want to show that the rank is 2, so we have to check that the columns of this matrix, which are sigma theta q and sigma tq, they are linearly independent. In order to do this, we can use the fact that this is equivalent to say that the cross product is a non-zero. So you can prove that the cross product is a length equal to x of t times the length of gamma prime t, and by the first of the assumptions we made, we get that this is positive, and by regularity this is also positive, so this is non-zero. So this implies that the rank of the sigma q is 2. I want to mention two special cases of surfaces of revolution. The first one is the cylinder. You can obtain the cylinder by rotating a curve whose trace is this one. So in this case we have that x of t is a constant, for example is equal to 1, and the z of t is equal to t. Of course this is not the unique possibility, but this is the simplest one. And the second of course here t can vary in r. And the second one is the sphere. More precisely, the sphere minus the south and the North Pole. So in this case, you can get the sphere minus these 2 points by rotating this curve. So you can choose x of t to be sinus of t and z of t equal cosinus of t. So remember, the z-axis is the horizontal one and the x-axis is the vertical one. And you can take t in 0 pi. Okay, now we study another class of surfaces known as level sets, and we will see which of them are regular surfaces. Okay, I need one definition, actually two. So definition 3.26. So let U be an open set over 3. F a function with real values and defined on U, which is smooth, lambda in R, a point in the image of F. Then 1, the set F inverse of lambda defined as the set of points in U such that f of p is lambda, is the pre-image of lambda, and 2, lambda is a regular value if f for all p in f inverse, of f for all p in f inverse of lambda, the Jacobian matrix at p is not the zero matrix, that is, if dfp, which is given by df dx at p, df dy at p, df dc at p is different from 0, 0, 0. This says that the gradient of f at p for each p in the preimage of lambda must be non-zero. We have the following theorem. Under the same hypothesis, of previous definition, if lambda is a regular value, then the preimage f inverse of lambda is a regular surface. Okay, let's prove it. The idea of the proof is that we will show that locally F inverse of lambda is a graph. Okay, so let's denote S. So let's denote by S F inverse of lambda, and let P a point of S. By hypothesis, lambda is a regular value, so the gradient of F is non-zero, so df dx at P, df dy at P, df dz at P, this is non-zero up to a change of coordinates, up to a change of coordinates. We can assume that, for example, df dz at P, this is non-zero. Let's define an auxiliary function defined on U with values in R3, where U is open set, which appears in the definition 3.26. The definition of psi is the following: psi of x, y, z. This is x, y, f of x, y, z. In order to facilitate the comprehension of what I'm doing, you can think of the function f as the temperature of a point of coordinate x, y, z. So if you do so, how does psi behave? Psi replaces the third coordinate of a point with its temperature. Now let's try to compute the Jacobian matrix of psi. D psi P is easy to compute. It is given by 1, 0, 0, 0, 1, 0. df dx at P, df dy at P, df dz at P. This is a matrix of determinant equal to df dz at p, which by hypothesis is non-zero. So this is an invertible matrix. Then by the inverse function theorem, there exists a neighborhood I will call it U tilde of P, and a neighborhood W of psi of P, such that the restriction of psi to U tilde is invertible. And its inverse is smooth. So how C inverse looks like? Psi is here, so it's easy to construct the first two component functions of psi inverse. The difficult one is the third one. So since psi replaces the third coordinate of a point by its temperature, I can write psi inverse of x, y, t as x, y, and I will write psi inverse z of x, y, t, where this is not the derivative with respect to z, but it is the third component of psi inverse. Here, psi inverse z of x, y, t is the unique value of z such that x, y, z belongs to U tilde, and f of x, y, z is equal to t. So in other terms, psi inverse z is the height of the unique point such that its temperature is T. Okay, now we define U as the set of points of coordinates x, y such that x, y, z is in U tilde. So essentially this is a projection of U tilde on the xy plane. Now we define, and clearly this is an open set because U tilde is open. And we define H from U to R as the function which associates to the point of coordinate xy psi inverse z of x, y, lambda. That is this function here evaluated at x, y, lambda. So in other terms, this is the unique height this is the height of the unique point in U tilde above xy, where the temperature is lambda. Now let's consider S intersection U tilde. S intersection U tilde is the set of points having this form. Why? Because H has been defined this way, and the surface S is the pre-image of lambda. Okay, so this says that S intersection U tilde is the graph of H, implies it is diffeomorphic to its domain, which is U. This is consequence of lemma 3.17. So in conclusion, we prove that S intersection U tilde so we proved that S intersection U tilde is a neighborhood of P, which is diffeomorphic to an open set precisely U in R2. Since P is arbitrary, then we have that S is a regular surface Okay, a bit of terminology. F inverse of lambda is a level set of F, and according to the theorem, if lambda is a regular value, F inverse of lambda is called level surface Let's consider one example. Let f be the function defined on a tree with values in R, given by this formula. Let's compute Jacobian matrix of F at P, the point of coordinates x, y, z. So we have df P is df dx at P, df dy at P, df dz at P, that is twice x, twice y, minus 2z. So it is immediate to see that this is 0. df P equals 0, 0, 0. If and only if P is the origin. So the origin belongs to the level set F inverse of 0, which is not a regular surface. Why? Because 0 is not a regular value because of this problem here. Instead, F inverse of 1 and the F inverse of minus 1 are level surfaces. So I want to remind you that this means that they are regular surfaces. Precisely, they are known as hyperboloid, of one sheet, and the hyperboloid of two sheets respectively. Okay, now I will introduce another class of surfaces. They are known as parametrized surfaces, and we will see what is the relation between a parametrized surface and a regular surface. So, definition: (3.28) parametrized surface is a smooth function sigma defined on an open set of R2 with values in R3 such that for all Q in U, d sigma Q has rank 2. So it is immediate to check that there is a profound difference between a parameterized surface and a regular surface. A regular surface is defined as a set, instead a parameterized surface is defined as a smooth function. Okay, what is the relation between I prefer to write relationship between parameterized surfaces and regular surfaces. We can say two things. The first one is that every surface patch for a regular surface is a parameterized surface. This is immediate to check. The second thing is provided by proposition 3.29. It says that if sigma defined on U with values in R3 is a parameterized surface, I will write PS, then for each point Q0 in U, there exists an open set U tilde containing U and containing Q0 such that the image S equals sigma of U tilde is a regular surface covered by the restriction, by a single surface patch, which is given by the restriction of sigma to u tilde. Okay, let's try to prove this result. Which says that every parameterized surface locally is a regular surface. Okay, proof. So let Q0 be a point of U, then choose a vector n in R3 with n not in the span of sigma u q0 sigma v q0. This is a space of dimension 2 because by definition sigma is a parameterized surface and consequently sigma is a map whose derivative has rank 2. Let's introduce the function f on u times r with values in R3, defined by this formula f of qt equal to sigma q plus tn. We set P0 to be the image of Q0 by sigma, and by definition of F, this is also F of Q0, 0. Let's give a look at the differential df at q0, 0. The differential of q0, 0, sorry, the differential of f at q0, 0 is a map which sends the basis E1, E2, E3. This is orthonormal, the standard orthonormal basis of R3 to the basis sigma u q0, sigma v q0, and this is a basis because of this hypothesis. You can check that this is true writing down the matrix which represents the f at q0, 0. and you will see that it's a matrix whose columns are given by the vector sigma uq0, sigma vq0, n. So this is this matrix is clearly invertible. Then we can use the inverse function theorem by the inverse function theorem. There exists a neighborhood of q0, 0 in u times r which is contained in R3, in the neighborhood I need to use I need to give a name to these neighborhoods. So the first one is A, the second one is B, of Q0, no, P0, sorry, in R3, such that F from A to B is a diffeomorphism. Okay, up to taking a smaller a, I can assume that A is a set having the following form: u tilde times minus epsilon, epsilon, with epsilon positive, and u tilde containing u and containing q0. Okay, remember that our goal is to prove that we have a regular surface locally covered by one single surface patch. So define S to be sigma of u tilde since F is a diffeomorphism. So F diffeomorphism implies sigma injective on U tilde, and this implies that there exists an inverse sigma tilde inverse from S with values in U tilde. We have to prove that sigma inverse is smooth. Okay, this is a bit complicated. So let P from A into U be the projection defined by this formula. This is possible because we are assuming that A is a U tilde times minus epsilon epsilon, and U tilde is contained in U. So essentially this is a projection of the first component. So what happens if we look at P composed with F inverse? P composed with F inverse is defined on B because F is defined on A and takes value in B. And this function here takes values in U tilde. Why? Because we define the projection this way, and A is this structure. So P, I wrote here P as a function from A into U, but I could be more precise and writing U tilde here, because A is the set having this structure. This function agrees with sigma inverse on B intersection S. I need to work with B intersection S because this is a function defined on B and sigma inverse is defined on S, so I have to work on the intersection. And it is smooth. And it is smooth. Why? Because the projection is a smooth function and the F inverse is smooth. So this proves that the sigma inverse is smooth and is done. Okay, let me check how much time I have. Okay, 10 minutes. The next topic I will present is the following: tangent planes. We have the following definition. So let S be a regular surface, then a regular curve in S. So this is a curve in a surface, means a regular curve in R3 whose trace is contained in S. Second part of definition, the tangent plane to S at the point P in S is the set of all initial velocity vectors of regular curves in S passing by, no, let's write with initial position P. The notation that we use for the tangent plane is this. We write T, P, S, and this definition here says that this is the collection of gamma prime 0, where gamma is a regular curve in S, whose initial point is P, with gamma 0 equal P. A vector is said to be tangent to S at P if it lies in TPS. Now let's see the characterization of TPS in terms of a coordinate chart sigma defined on U open set over 2 with values in S. Sorry, I should write with values in V contained in S and P in V. If we set Q to be sigma inverse of B and UV are the coordinate variables on U, then we have the following lemma. TPS is the span of sigma UQ, sigma VQ. In particular, this implies the dimension of TPS is 2. Okay, let's prove this statement. Okay, remember what is V? V is the open set in S on which sigma takes values. So sigma takes value in V and it is defined on U. Now, since the definition I gave before, definition of regular curve in S is local, then instead of working with regular curves in S, I can work with regular curves in V, up to taking the restriction of a curve to V. Then, since sigma is a diffeomorphism, the regular curve in V are sorry, I omitted something with the initial position P are composition of regular of sigma with regular curves in U with initial position Q. Let's try to make a picture. Q is a sigma inverse of P. So this is a U, this is sigma, and this is a V containing S. This is P, this is Q, and what we are saying here is that a curve with initial position P in V is the image by sigma of a curve with initial position Q in U. So we have to prove now this statement. Okay, now we use the proposition (3.7), which says that the differential of a map define an open set U in Rm with values in Rn is smooth. Then dFP at V is given by F composing gamma prime at 0, where gamma 0 is P, gamma prime 0 is V, and gamma is a regular curve. Okay, let's start from TPS. So TPS by definition is gamma prime 0 such that gamma is regular in V with gamma 0 equal P. But this is according to what I erased. This is sigma composed with beta prime at 0. So any curve of this kind is the composition of sigma with a curve in U, where beta is regular in U with beta 0 equal Q. This follows from this picture. But this proposition says that this is nothing but then the image of the sigma at Q. But the image of this sigma Q, we already know it is a span of the two columns of the matrix representing this map. And they are sigma U at Q, sigma V at Q. And this is the end of the proof. So we prove that TPS coincides with the span of these two vectors. Okay, that's all for today. Thank you for your attention.